All right, in this lesson we're going to look more about the consequences of our magnetic force being given by QV cross B. And the first consequence that we see, and one that is really important for you to get down into your annotations, is that the magnetic force will always be perpendicular to the V vector because it will be perpendicular to the VB plane. The consequence of this is that the magnetic force will never have any part of it pointing with the V vector or against the V vector. So it will never change the speed of the charged particle. It will push and pull it, it will deflect it, but it will not change the speed. If it does not change the speed, it will never change the kinetic energy. And now we have our domino effect. Since it never changes the kinetic energy, we know the work kinetic energy theorem, work done equals the change in the kinetic energy. The work done by the magnetic field on a charged particle will equal zero always. So no matter what is going on in a problem, do not ever let yourself lapse into the notion that, well, this problem's different. In this one, the magnetic field is going to do work. No, it won't. So the fact that we have situations where magnetic fields we'll see like railguns you may have heard of can push or pull the particles and speed up those particles in those situations is separate from what the magnetic field does to an individual Q. So again, no matter what the question is giving you, do not lapse into the notion that the magnetic field does work. For the AP test, that should be the easiest question for you to answer. If they're asking you about the work done by the magnetic field, you look down in your multiple choice, you see zero, you circle it. Okay. What does the magnetic field do? Well, let's take a look at the example on this page, and this is going to take a little bit of discussion. So that's okay. Please take your time, annotate everything on this page, pause it, rewatch it, ask questions in class. It's important that you understand this page of notes. What we're looking at here is three regions of space. We have one region of space where the B field is zero, so no magnetic field. So a charged particle in this case is going to come streaming along. The electron, we're going to say it's an electron, comes streaming along with some speed v. Doesn't matter what the speed is at the moment. So we have a velocity vector v straight along the x-axis. We are not going to say where it comes from or care where it comes from, but we're going to say there's a uniform constant magnetic field in this middle region of space, and then again no magnetic field in this right-hand far region of space. And what's more, we're going to pretend that we have control over this constant magnetic field. So in other words, I can flip a light switch and shut it off, and then flip a light switch and turn it back on. So maybe generated by an electromagnet. So we'll talk about how that's very easy, very possible to do this in actuality. We're going to see how the magnetic field very quickly, using QV cross B, is going to act as a deflecting and protecting force if this charged particle is highly charged and we're in its line of fire. So if we are here worried that this charged particle is going to come impact us, it's going to come straight through and hit us. Well, without the magnetic field, that's exactly what it would do. And what we are going to now do is take a look at what happens, or what would happen, if, let's say, our light switch was off, so there's no magnetic field in the center, and the particle's coming along, and right when it gets to the middle, we're going to flip the light switch on, and we are going to generate this magnetic field out of the paper. Remember our arrows our archery arrows with points coming at us means it's out of the paper, and of course if we see the feathers of the arrow going into the paper, it's going away from us. So in this case, the B field is coming straight at us. We are going to do QV cross B. We are going to pretend that the Q is a positive Q and do our cross product and then reverse our thumb because it's a negatively charged particle. So it's a little bit of a contortionist. So convince yourself, take a moment, pause the video if you need to do QV cross B. So we have QV, V is to the right, B is out of the paper. If you take a moment and do your right hand rule, so if you're right-handed, put down your pencil, use your right hand, QV cross B should give you, if you're doing it correctly, and we can talk about this more in class if you're not remembering correctly how to get the QV cross B. So normally, QV cross B, positively charged Q, would give us thumb down. We reverse it and put our thumb up. So the magnetic field will be perpendicular to the V vector, and in this case, straight up. So that means it's going to pull the particle up a little bit. Well, if you do QV cross B again, that would give you a thumb radially out, and you would flip your thumb radially inward. So please take the time to actually do it. Use your pen as the B vector coming out of the paper if you need to. Hold it up to your page. Do your QV cross B with your right hand to get the FB vector out of the circle and then going radially into the circle. And that is where, now I hope you can now see that you have this circular type motion or partial circular motion of the particle. So a couple of things is possible. One is that if the B field is strong enough and or wide enough, right? So if I have enough room or the B field is simply strong enough, it can totally capture this particle and trap it in this region of space and spin it around. So I have a particle confinement situation. I've confined it to this B field. It's spinning around, it's not gaining speed, it's not losing speed. It's just trapped in this magnetic field. Now, if the B field were weak and the particle ran out of room, it would deflect along this circular arc. The speed would not change because B fields do not do work. So no change in the kinetic energy, and it would shoot out. But you can see here how it has protected us, the magnetic field of the Earth, and this is essentially how the magnetic field of the Earth protects us, by deflecting these particles away from the Earth and going around us and then contributing to the magnetic field in that tail that we were talking about earlier. So we will always be looking at the magnetic force as a circular motion force or a partial circular motion force where the particle is trying to spin in a circle. Either it is spinning in a circle or trying to spin in a circle based on what the magnetic field is doing. So again, we will be talking more about this in class, and we're going to start doing some homework problems as well with circular motion shortly. But a very important page of notes, cross product direction and reversing the thumb if it's a negatively charged particle is there. The notion here that the magnetic force is not doing any work is important. So we really need to discuss this if these concepts are not clear to you.